Good morning, guys, and today we are going to do a continuation on this idea of kinematics just to have a clear picture of what you're expected to do in any problem that has to do with acceleration. So, uh, we will start with a very simple thing. I want you to consider the following situation. Imagine this idea. Imagine that you have an object that starts at rest and it accelerates for 12 seconds at a rate of 4 meters per second squared. What sort of thing would you want to know about an object like that? Well, one of the things that you might want to wonder is what will its final velocity be? What will be its final velocity? And then the second one, how much has it displaced? And of course this is supposed to be a question, so let's say that this is the problem that you are faced with. An object starts from rest, accelerates for 12 seconds with a rate of 4 meters per second squared. You want to know what is the final velocity and you want to know how much has it displaced. So in order to solve a situation like this, we need to use the kinematics equations you've been studying. Let's do it with a new note, and in this case it might be useful to have a square grid just to be able to picture things out clearly. First of all, the very first part of any solution that you want to do is something called your data list. And in your data list, you are going to have, in this type of problem, 5 possible variables. You might know them or they might be unknown. One of them is the displacement, the other one is the time, then you have the initial velocity of the object, the final velocity of the object, and finally you want to know what is the acceleration. So in any kinematics problem you have 5 variables. Now in this situation, those 5 variables are not all known. You don't know how much the object moved, and you don't know what is the final velocity of the object. Now if you consider a possible motion diagram, that's the second part of your solution. You want to know a motion diagram. You will see that this object is moving faster and faster as time goes by. It started from rest, and so your first points are very close together. And then as time passes, they move farther and farther apart until eventually you end up with a graph like this. And that's your motion diagram. That motion diagram is telling you basically that your initial velocity was 0, you have some unknown final velocity in the positive direction, and as time went by, that velocity was increasing in size. Of course, it also means that you have an acceleration in this direction, and you don't know how much that is. Therefore, if you want to take a clear picture of what's going on with your solution, look at this. You have a data list over here, and you have a motion diagram. It might seem like a trivial thing, but the motion diagram is very, very important because it forces you to think on what the solution might be. Finally, you do have some data for this problem. They told you that it moved for 12 seconds. They told you that it started from rest, so even if it's not a number, it gives you a number. The initial velocity is 0 meters per second. And they told you that the acceleration was 4 meters per second squared. So that's information that you may want to use. In the first case, if you want to know the final velocity, you can see that this probably involves the acceleration, final velocity, because that's what you want, initial velocity, and time. And there is only one equation of the 5 that has those 4 things, which is equation number 1. So your acceleration is equal to the change in velocity, final minus initial, divided by the time interval. A little algebra tells you that the initial velocity plus acceleration time is equal to your final velocity, and therefore your final velocity is 48 meters per second. And that is your first answer. So you see, there wasn't so much to that. You already have one item crossed out. Now, for the second part, things are not so easy because you still have to decide which equation you're going to use. Now, it is always a temptation to take this final velocity and try to use it. You have to fight against that temptation. You have to try and use only the values they gave you, which in this case are acceleration, initial velocity, time, and the one that you want, which is displacement. Now, which is the formula that doesn't have final velocity? Well, that's easy enough. The one that doesn't have final velocity is displacement. Oh, sorry. I want black. Displacement is equal to initial velocity times time plus 1/2 times acceleration times the square of time. And you don't even need to solve for any variable. It's already solved for the displacement. So 0 times 12, which doesn't add anything because it's 0, plus 1/2 times 4 times 12 squared. So this is 144 times 2. Final answer, 288 meters. Notice, please, that you got meters per second squared and you're multiplying them times the square of seconds, and so things cross out or cancel out, and all you're ending up with is meters, and therefore that is your final answer. So To summarize, you basically have three very important steps in your solutions. First, you need your data list. Second, you need your motion diagram. And finally, third, you need an algebraic solution. And in order to get that algebraic solution, you need to choose your formula wisely by looking at what you know and what you want to find out. So, be safe, keep working, and you'll get it. Practice enough. See you.